Hi everyone, my name is Tyler McCorn and I'm a PhD candidate at the University of Western Australia and the Australian Research Centre for Transforming Maintenance through Data Science. This presentation will be looking at a value-driving use case of technical language processing. Currently, there doesn't exist many well-established means of demonstrating the value that technical language processing can provide to industry. So in this work, we propose and explore the use of technical language processing for the semi-automated estimation of reliability measures for maintenance work order records. Currently, industry as a whole faces a wide set of challenges that predominantly stem from the human-centric nature of tasks performed in technical settings, such as statistical life data analysis. Due to this human-centric nature, many of these tasks are not only slow and tedious, but not amenable to scaling. They lack reproducibility and standardization, as well as require significant tacit knowledge that is held by subject matter experts. As a result, it wouldn't be atypical to imagine the situation where a handful of reliability engineers are provided the same set of maintenance work order records for statistical data life analysis, and they all produce a broad range of different outcomes. These challenges are characteristic of industry at large and highlight the difficulty that is faced by practitioners when trying to liberate knowledge from semi-structured electronic documents, such as maintenance work order records. Furthermore, it inhibits the development and eventual adoption of semi-automated or fully automated data-driven processing strategies within industry. However, technical language processing is well positioned to overcome these challenges and unlock value for practitioners and ultimately industry. In this work, we propose and explore the acquisition of evidence for mean time between failure estimation for pump assets through the use of a pipeline developed with technical language processing principles. This is motivated by the fact that up-to-date reliability measures are crucial for maintenance strategy validation and optimization. Using this pipeline, we were able to emulate a prototypical reliability engineer to assess the impacts that decisions made when processing maintenance work order records have on resulting reliability measures, which in this case is mean time between failure for pump assets. We explored this as the task of statistical data life analysis currently encounters many of the challenges previously mentioned. To gain insight into these impacts, we used two large industrial datasets acquired from organizations operating in the mining and mineral processing industry in Western Australia. As seen on the left-hand side, the two datasets are composed of 15 and 90,000 maintenance work order records, respectively, with each coming from dissimilar computerized maintenance management systems. On the right-hand side, examples of typical unstructured free text data fields that are classified as maintenance work order descriptions are shown. In this work, the unstructured fields are used to identify lexical units, such as words or phrases, that are indicative of end-of-life concepts for identification of evidence for parameter estimation. Even though the composition of these samples are quite different, we show that it isn't a significant barrier for our technical language processing pipeline to elicit knowledge from. Here we can see the pipeline developed with technical language processing principles that is used to emulate a prototypical reliability engineer and assess the impacts made when processing maintenance work order records. Unfortunately, due to the time constraints, I cannot go into the technical depth of the pipeline methodology, but this work will be submitted to the 6th European Conference of the Prognostics and Health Management Society that will outline it in more detail. Additionally, to support reproducibility in technical language processing research, we're releasing all of the accompanying code to be openly accessible for use by researchers and practitioners. Our pipeline consists of two stages. The first stage uses well-established techniques from the field of natural language processing, namely self-supervised co-occurrence-based word embeddings and frequency-based collocations. Once captured, they are used to build a domain-specific gazetteer that is essentially a conceptual dictionary that is used to map the concept of end-of-life to information within maintenance work order descriptions. This is an expert-in-the-loop process that uses an expert to iteratively select and validate domain-specific end-of-life terms. The second stage of this pipeline uses structured fortuitous data fields in maintenance work order records to discriminate whether identified end-of-life events have likely materialized and are valid as evidence for statistical data life analysis. In this pipeline, domain logic is dictated by criteria set by the practitioner or organization. With this pipeline established, we were able to use it to emulate the impacts of decisions made by a prototypical reliability engineer. To achieve this, we use scenarios that attempt to model 3 plausible types of engineers, each which can be depicted as identifying evidence for parameter estimation using spreadsheet software. The first scenario involves using only a single keyword or phrase to identify evidence. The second uses an exhaustive vocabulary of words and phrases to identify this evidence, whereas the third uses both an exhaustive vocabulary of terms indicative of end-of-life events, but also available structured fortuitous data fields, such as time, financial, and resource information. To evaluate the efficacy of the proposed pipeline, we used the third scenario on the entirety of both datasets to determine how well it could classify end-of-life events in maintenance work order records. After constructing the end-of-life gazetteer and running the pipeline, we found that it was able to elicit initial mean time between failure estimations for 10 to 20% of the assets in each dataset in under 2 minutes. To put this into perspective, it would be impossible for a reliability engineer to perform the same task on the same number of assets in this amount of time. To better understand the pipeline's classification ability, we randomly sampled 20 assets, IID, from both datasets, consisting of hundreds of maintenance work order records, and performed human evaluation with 2 domain experts, where it was found that the pipeline's performance was better than expected, achieving nearly 80% F1 score on the first dataset. However, it was also found that the results were largely dependent on the availability of structured fortuitous data fields and the underlying maintenance strategy of the organization. But nonetheless, this pipeline highlights the value that technical language processing can provide for this particular task. With the efficacy of the pipeline established, we used it to gain insight into the impacts of decisions made when processing maintenance work order records for statistical data life analysis. Here we selected 3 of the most populous assets from each dataset, which consisted of centrifugal, piston, and peristaltic pumps, and applied the 3 scenarios to each. Due to time constraints, we pay attention to the cells highlighted in green, which correspond to the centrifugal pump in the first dataset. Here we can see that the variation in mean time between failure is significant, varying up to 220% depending on the decisions made when processing records and information available when performing this task. This observation, while rather extreme, highlights an important challenge that exists within technical settings, which is the sensitivity of measures that rely on complex information and tacit knowledge. In this instance, large fluctuations in mean time between failure estimation can have real impacts in day-to-day operations. For example, overestimation of mean time between failure estimates can result in unexpected downtime, as preventative maintenance schedules will be less frequent and unwanted corrective events may occur, resulting in drains of people and resources from scheduled work. On the contrary, if mean time between failure estimations are too low, then maintenance budgets may become overcapitalized due to an increased need for maintainers and parts to perform unnecessary work. These observations make it clear that technical language processing is necessary to provide improvements in standardization, transparency, and reproducibility for tasks in technical settings, as the current human-centric nature of these tasks is challenged in their current formulation. With these results in mind, our pipeline has provided insight into the sensitivity of results produced when processing records for statistical data life analysis. It also proved to be both a scalable and fast process, processing up to 90,000 work orders with 3,000 assets for initial mean time between failure estimates in 10 minutes end-to-end without significant subject matter expertise required. As the pipeline is both programmatic and deterministic in nature, it is inherently transparent, consistent, and standardized, with all decisions being made easily interpretable, reversible, and explainable. However, with all research comes caveats and limitations. The main caveat of this work is the need for structured fortuitous data fields and expert logic to reason about the end-of-life events to facilitate semi-automated reliability measure estimation. The main limitation of this work is that it's only been applied to the individual asset level and not systems or subsystems. Although future work is currently being addressed by researchers within the first theme of the Australian Research Centre for Transforming Maintenance through Data Science. This work includes an increased applicability to systems and subsystems, improved reasoning over unstructured data fields using modern information extraction techniques and hierarchical reasoning, and further reductions in the need for time investment by subject matter experts. I hope that this presentation has demonstrated the value that technical language processing can provide through the use case of semi-automated reliability measure estimation from maintenance work order records. Thank you.